So far we have seen combinational circuits in this course on digital circuits. Next we will be looking into sequential circuits. So, in sequential circuit what happens is that there is a sequence of events that can take place. Maybe you do not change the primary input, but still with the passage of time the situation in the circuit changes. So, typically if there is a moving display, then we get some characters on the display for some time, then after some time some other characters gets displayed. So, that type of systems there is a sequence of events that are taking place. So, this type of devices or this type of systems, they are known as sequential digital systems. So, for the circuit design behind that, so they will be coming under this broad heading of sequential circuits. So, sequential circuits are digital circuits in which the outputs will depend not only on the current input, but also on the previous state of the output. So, it is not only in case of combinational circuit, like if we take one AND gate. So, the AND gate output is determined by the input combination that you feed at this point of time. So, it is not dependent on whether the AND gate was previously 0 or 1, but if you give say 0 0, then the AND gate will always produce a 0, or if you give 1 1 irrespective of the previous output of the AND gate. So, it will produce a 1 value. However, in case of sequential circuits, so that may not happen, because the output will also depend on the previous state of the output. So, these basic sequential circuits can be divided into two categories. One category is known as level sensitive, another category is known as edge triggered. So, level sensitive means like when we are looking at the operation of the circuit. So, when are we expecting the circuit to change its state? So, it may be that we want during some interval of time, or we may want it at some precise instant of time. So, if I for example, so if I draw a signal, so which is in sequential circuits, so that is commonly known as clock signals. So, if I have got a signal like this, okay, so it has got a high period and a low period. So, you see this signal, it has got some portion of the signal where the value is high, and there are some portion where the value is low, and there are some other portions, other points of interest. Maybe this is a point of interest when the signal is going from high to low. Similarly, say this is another point of interest, so where the signal is going from low to high. Now, if we say that we are interested about the system behavior when this particular if this is the system, if this is the system that we have designed. So, this is the and it has got a number of inputs and number of outputs, and there is a special signal which is commonly known as the clock signal, where we feed an input pattern like this. Okay. Now, we may be interested in the behavior of the system when this clock signal value is high, or when the clock signal value is low. So, when this thing happens, so when we are interested about the behavior of the system when the clock signal is high, we say the circuit is high level sensitive. Similarly, if we say that we are interested about the system behavior when the clock signal value is low, so we say it is a low level sensitive. And as I have said, the other type of option is when these edges occur. So, it may be that we are interested about the system behavior when the clock signal makes a low to high transition. So, this is called a rising or positive edge triggering, and in case of this signal, if we are interested about when the signal is falling down. So, if we are interested in that type of situation, then we will say that the system is considering falling edge triggering. So, or the system is a falling or negative edge triggered system. Now, depending upon our requirements, so we can design a system to be a level sensitive one or an edge triggered one, and between them also we can think about high level sensitive, low level sensitive, or rising edge triggered, falling edge triggered. So, depending upon the requirement, so we can design the circuit. Now, another possibility is that we are interested in both of these events, that is this falling edge as well as this rising edge. So, we are interested about the system behavior when the clock signal is rising or the clock signal is falling. So, this type of systems, so they will be known as dual edge triggered system. So, in this part of lecture, so we will slowly look into all these different categories of sequential circuits and how to design those circuits. Now, coming to the basic sequential circuit. So, this is a sequential circuit. So, since it remembers the previous state of the signal of the system. So, there must be some memory element in it. So, you see that there are some memory elements in the system. So, if you forget about this part, this memory element, then it has got some input and it has got some output. So, that part is a pure combinational circuit, but as if this combinational circuit, it has got some further input coming from the memory elements. And this combinational circuit, it can also be divided into into two parts. For example, one part is determining this thing from input and this previous state from the memory element values. So, it determines the output. Another part is from the input and this memory element value, it determines the next value of the memory elements. So, as a user of the system, so these memory elements are not of interest for us. So, we are bothered about these outputs only, but since this memory element inputs are also coming to this combinational circuit. So, what will happen is that this combinational circuit output will depend not only on this present input, but previously what was the content of the memory element. So, that will determine the output. So, that is the sequential behavior. So, it remembers what was the previous state of the system. So, these memory elements, so they are also known as the state values. They are also known as the state values. So, the state values of the signal of the system is remembered, and then when this next input comes, the state values are also taken into account to determine the output. So, we will so that way we can think about these sequential circuits to be consisting of the basic combinational part and a set of memory elements. Another type of categorization that we can have in case of sequential circuit is synchronous sequential circuit versus asynchronous sequential circuit. So, in case of synchronous sequential circuit, circuit output changes only at some discrete instants of time, and this type of circuits they achieve synchronization by using a timing signal called the clock. So, so just some time back I have already introduced the signal clock. So, naturally the question comes, can we have a sequential circuit that does not have any such timing signal like clock? Okay. The answer is yes, there can be. So, for the type of sequential circuits where we have such a distinct clock signal, so they are known as synchronous sequential circuits. On the other hand, there is asynchronous sequential circuit where there is no concept of clock. So, there is no clock and the output can change at any point of time. In case of synchronous sequential circuit, so the output can change only at the clock boundaries, maybe for level triggering it may be at when clock is high or clock is low, depending upon whether it is high level triggered or high level sensitive or low level sensitive. On the other hand, if it is edge triggered, so if it is whether it is rising edge triggered or falling edge triggered. So, based on that only at those points the circuit output can change, whereas for asynchronous circuit the output can change at any point of time. So, we will see some example. So, this is the typical structure of a synchronous sequential circuit. So, we have got this combinational input, combinational circuit that gets the input, plus there are some memory elements, so which are commonly known as flip flops. So, we will see these flip flops after some time. So, these flip flops are there. So, these clock pulses are actually feeding these flip flops. So, these flip flops are activated when the clock signal is active. So, if we say it is high level sensitive, then when the clock signal is high, that is at this point, then only the values that are coming from the combinational circuit to the flip flops will be stored in the flip flop. Otherwise, when the clock signal is low, for example, during this period, whatever happens to this combinational circuit, so these lines will be changing, but that will not affect the flip flops. So, as a result, the state of the circuit will not change, state of the circuit will remain unaltered. Only if when the clock signal is active, then the input changes, then only these flip flops will change. Similarly, if we are thinking about say edge triggering, then if we say that it is rising edge triggered, so the circuit state will change only if the input changes around this. So, the input changes around this time, then only the circuit the state out this flip flop contents will change, otherwise it will not. So, this gives us advantage because the design becomes simpler, as we will see. However, in some systems, so we may not have this type of clock signal, and they are known as asynchronous circuits. So, this asynchronous sequential circuit, so this is an example. So, here you do not have any clock signal in the system. However, if I ask you, suppose I give a equal to say 0 and sorry, if I give a equal to 0 and say b equal to 0, a equal to 0 and b equal to 0. So, can you tell me what is the value, what is the output? So, it is difficult because a equal to 0, b equal to 0 means these two bits are getting 1 1. So, it is dependent what was the previous value of this out. So, it is dependent on that. So, until and unless I tell you what is the previous value of this out, you cannot determine the next value of out. So, naturally, so this type of circuits, this is also a sequential circuit because it depends on the previous value or previous output of the circuit. However, there is no explicit clock signal in this system. So, it is not a synchronous circuit. So, this is an asynchronous circuit. So, these asynchronous circuits are also used sometimes. So, we will see the relative advantages and disadvantages of these two types of systems. So, applications of synchronous. So, this synchronous sequential circuit, they predominate asynchronous sequential circuit. So, normally whatever sequential circuits we design, so they have a clock signal in them, and then most of the circuits are synchronous in nature. So, you will not find much asynchronous sequential circuit because of several reasons that we will see, and this typically used to perform activities that need to happen at precise times. So, at some regular time interval something has to happen. That example that I took at the beginning, like if there is a display, then some character is displayed. So, there is a fixed amount of time for which one character will be displayed, after that the next character will be displayed. So, this passage of timing, so when the character will change, so that is that is fixed. So, we can say that at fixed intervals of time we are expecting something to happen and something to happen in the system. So, they are synchronous systems. So, they are typically used to perform activities that need to happen at some precise times, or if there is a conveyor belt on which items are moving and at regular intervals of time. So, we can there may be a robotic hand which is picking up the items from the belt. So, that also happens at some regular intervals of time. So, all these examples, so they will be leading to synchronous sequential circuits. On the other hand, asynchronous sequential circuits, so they have got applications in signal processing, because we do not know when the exact signal will what is the clock of the clock period of the arrival of this signal. So, that is not known. So, we have to we have to do it in an asynchronous fashion. Then one typical problem with the synchronous circuits is that, so the speed of the circuit is bounded by the clock signal that you are feeding. So, this clock, if the clock signal is not very high, so you cannot do operations fast. So, I may have different components in my system. So, they are operating at all of them are synchronous sequential circuit. Then the delay of the slowest module, so that will determine the maximum clock frequency that I can have for the system. Whereas, if all these systems are asynchronous in nature, then what can happen is that all the systems, they can operate at their own speed, and we may get a faster system. So, maybe you can design an arithmetic unit which is much faster than this register and all in the system. So, that way you get a fast arithmetic unit. Then simple microprocessors, so they are made asynchronous because of this speed achievement. So, we can do it like memory, the static memory, then this RAM, FIFO, first in first out buffers. So, they are all made they are made of asynchronous system. ILIAC 4 machine, so this is one of the early computers. So, they are made in asynchronous mode. Now, why do we go for synchronous then? The asynchronous has got so many advantages. The major advantage is the simplicity. So, asynchronous system, so since we have to consider what is the previous value of the output at any whenever we are trying to determine like what is the current value of the output, we are faced with the question that what is the previous value of the output. Now, this previous value means before how much time. So, that question has to be answered, and in case of synchronous sequential circuit, so you can just say it is at the previous clock period what was the situation, or previous to previous clock period what was the situation. So, we have got a fixed interval or fixed instant of time at which of which we are talking about, but in case of asynchronous circuit, so we do not have this instants of time. So, that they are the time becomes a continuous value there, and then this previous time definition of this previous time becomes difficult. So, synchronous circuits are generally much simpler to design and they are widely taught and understood. Okay. For the digital circuits classes, so we normally go to the synchronous design only, because that is much easily understood and can be easily taught. And in our course also for most of the designs, so we will be going to synchronous designs also. Available components, so there are many chips which are synchronous in nature. So, they are realizing some sequential circuit which are synchronous in nature. So, that is why we go for that. Then simple way to deal with noise and hazard. So, if some noise signal comes, so that can change the state of the system. Now, you see for synchronous sequential circuit, we have the advantage that if the noise does not come when the clock is active, then that noise will not be able to affect the system. So, we can concentrate only for noise protection during the clock active time. Similarly, hazard that we discussed in our previous classes. So, that also is that effect will come only when we have got this clock signal active. So, otherwise particularly for edge triggered system, so for very small amount of time we have to have the system noise and hazard free, otherwise this noise and hazard, so they are unable to affect the system state. What is the disadvantage? So, disadvantages of synchronous circuits are like this. It is sensitive to variations in physical parameters, because physical parameters like say if I have got a big circuit, then this the various parts of it they are operating at different speeds, and then with the change of this temperature and particularly this power consumption and temperature, those values are also changing, the delay values are also changing. So, that makes it difficult. So, that becomes sensitive to variation in physical parameters. It is not modular. So, you cannot just add another module to this, because that will determine the clock speed also. Power consumption. So, whenever the circuit is active, so it will consume power. Now, in case of synchronous sequential circuit, what is happening is that at least the clock signal is changing at regular intervals of time, and we have seen that for CMOS type of technology, the power consumption occurs only when the input signals change, the input signals are changing the values. So, as a result the output is also changing. But in case of sequential circuit, you know that even if we have got inputs unchanged, input remains same, so that output is also same, but the clock signal will always toggle. So, as a result the power consumption due to this clock signal will come into picture. So, the synchronous sequential circuit power consumption will be high. Clock distribution is difficult due to clock skew. So, clock skew means, so if I have got a board on which I have got some systems made. Now, the clock signal is entering here. So, I have got a chip here, I have got a chip here, I have got a chip here, and all of them are operating in a synchronous mode. Now, this clock signal is say distributed like this. Okay. If it is distributed like this, then you see that this delay of these paths, so they are proportional to the length. In fact, it is squarely proportional to the length. So, as the length increases, the delay increases severely. So, this it is intended that when the clock signal reaches this module, at the same point of time the clock signal reaches here and also reaches there. But the way I have laid out this clock line, so it will not be, it is not possible to ensure that. So, there will be a skew, the time at which the clock reaches here, this third module will get the clock after some time delay. So, this is known as clock skew, and it is so this clock skew, if it is there, then naturally when this circuit is producing some output, so it is to be used by this module, say functional output produced by the module 1 is to be used by module 3, and if it is so, then this module 1 it has produced the output when the clock signal was active, but at that time this module 3 was not getting the clock, so it could not use the value. By that time maybe some other thing has changed. So, that way that is why this clock skew is a severe problem, and for synchronous sequential design, so it is a challenge like how to distribute the clock signal through the through the integrated circuit chip. Okay, so, that is a VLSI layout problem. So, we will not go further into that. So, the clock distribution becomes difficult due to this clock skew. The maximum possible clock rate is determined by the slowest logic path in the circuit. So, if I have got some combinational circuit, suppose this is a combinational circuit and this is feeding some flip flop. Okay. So, this is feeding some flip flop, this output is stored like the way we have seen the sequential circuit. Now, what is the what type of clock I can apply to this flip flop. Okay. So, if this flip flop operates at a clock, so this combinational circuit it gets some input from outside, it does some computation and accordingly it produces the value here. So, if this clock is faster than the delay of this combinational block, then what will happen? This flip flop will get some wrong values. So, the values when I change these input values, the before the proper output has been computed, the flip flop will get the value. So, as a result the value will be incorrect. So, what is required is that this clock should be slower than the delay of this particular block, and there are several paths through this network. So, one path may be like this going through several gates, another path may be like this, another path may be like this. Now, among these three paths, so whichever path is the slowest, so that is the critical path. So, this critical path delay, so this will determine the clock frequency, the maximum clock frequency at which I can operate the system. Okay. So, the slowest logic path in the circuit, so that will determine, that is the critical path. So, it will determine the clock period. So, that is another problem with the synchronous sequential circuits. Asynchronous circuit, the major advantage that we get is the high performance, because there is no clock signal. So, I am not limited by the clock. So, I can operate whichever module gets the data ready. So, it can start operating on the data and produce the result fast. Low power dissipation. So, if the inputs do not change, then the output will also not change. So, as a result there is nothing like at every clock interval. So, there the clock toggling will occur. So, that sort of thing is not there. So, this power dissipation is often much less compared to the synchronous sequential circuit. Low noise and electromagnetic emission. So, this is also another issue, like this generally it is seen that it does not produce this high noise, and electromagnetic radiations are also less, because there is no such toggling. And good match with heterogeneous system timing, like if in a system I have got different types of components and they are operating at different frequency, then also we can have this thing. So, in fact, for this heterogeneous timing, so this leads to one particular type of structure which is known as GALS structure, which is globally asynchronous, locally synchronous type of structure. So, that takes the advantage of both this synchronous and asynchronous design. What the idea is that, so suppose I have got a system like this. Now, in this system I have got several components. So, this is one component, so this is another component, this is another component. So, they are interacting between them. So, there are some signal lines running between them. So, they are interacting. Now, they have got they are running at their individual clocks. So, this is running on clock C1. So, this is running at clock C2, this is running at clock C3, but the clocks are not same. So, C1, C2, C3 are not same. So, individually when you look at the system, so they are synchronous in nature, but if you look into the overall system, so that is a asynchronous system, because there is no common clock synchronizing all the three subsystems. So, this type of designs have become very popular, because it combines the advantages of synchronous design, that is the ease of design and all, and the advantages of this asynchronous design, where you do not have to have this global clock signal, then this power consumption, high power consumption like that. So, they are not there. So, that way this GALS style of design have become quite common. So, next disadvantage of asynchronous system is the substantial circuit level overhead, because of this a lot of feedback lines will be running since the clock signal is not there and these sequential elements are often realized by with the combinational elements. So, as a result there will be a large number of lines running backwards. So, that is the circuit level overhead is high, and the set of CAD tools. So, that is for asynchronous design. So, we do not have this very good CAD tools available so far. So, that is the other problem. And delay. So, delay in the sense that you have to match the delays between two stages. If both the stages are asynchronous in nature, so you need to match the delay between the two stages, and that also becomes a concern. Okay. So, delay becomes a concern. So, we will start with some latch circuit. The first latch that we will look into is known as the SR latch. The first sequential circuit that we will look into is known as SR latch or set reset latch. So, this is the most basic unit of sequential circuit. It has got two inputs S and R and two outputs Q and Q bar or Q dash. The two outputs must always be complementary, that is, if Q is 0, Q bar must be 1 and vice versa. So, this is by the specification of the SR latch. So, it says that it has to be a sequential circuit that will have two inputs set and reset, and there will be two outputs Q and Q bar, and by specification Q bar should be complement of Q. It is further stated that the S input will set the Q output to logic 1 and the R input resets the Q output to logic 0. That is why S is called the set input, R is called the reset input. So, the set input will set Q to 1 and reset input will set Q to 0. So, a basic circuit diagram for this can be like this. So, we can take two cross coupled NOR gates. Okay. Now, you can understand that if I set this in this NOR gate. So, if I set this S to be equal to 1, if this S is equal to 1, then this Q bar will be getting 0, and this so if it is 0 here, then whatever be the Q bar, so it will be coming here. So, this Q will be coming back this. So, this set and reset input. So, let us look into this truth table and try to understand. Suppose S and R both are 0 0. So, if both are 0, if both of them are 0, then what happens is, so this is 0 and this is 0. So, this is this Q is coming and this is a NOR gate. So, what will happen is that this Q, whatever be the Q value, so it will be coming at as a Q bar. So, this Q value will be coming and this is 0. So, NOR gate. So, it will be Q bar and this is Q bar. So, when it is getting this, so this is equal to, this will remain equal to Q. So, if you look into this truth table, when this S and R, so Q plus and Q plus dash. So, Q plus means what I mean is that at the next time unit what will be the value of Q. So, that is Q plus, and whatever and Q dash plus means what is the value of Q dash at the next time unit. Now, you see that what happens is that if you give S and R as 0 0, then this Q remains at Q plus remains at Q and Q dash plus remains at Q dash. That is whatever the value it was having previously. So, that value remains there. Now, let us take the other combination. Let us take, say, this S equal to 0 and R equal to 1. Then, since this is a NOR gate, irrespective of the value of Q bar, this Q will become equal to 0. And once this Q and this Q was coming here. So, this will be this 0 comes here. So, this 0 will be making it 1. So, you see that when this S equal to 0 and R equal to 1, we get the value Q plus equal to 0 and Q bar plus equal to 1. So, that is the reset. So, as if the flip flop has been reset or the latch has been reset. The other combination, like say 1 0. So, if I give S equal to 1 and R equal to 0, then what will happen? This will be setting this. By the similar logic. So, this Q bar output will be equal to 0, because this S input is 1, this NOR gate, and this 0 0 going there. So, this will make this thing to be equal to 1. So, what is happening is that Q plus is becoming 1 and Q dash plus is becoming 0. So, that is the value is set, and if it is 1 1, then it is we say that if I give it 1 1, then both the outputs will become 0 0, and by the specification. So, this is called illegal. So, this is illegal. So, we should not apply this 1 1. Similarly, if we take the NAND gate based realization also, so you will get, you will see that if we do it, take 2 cross coupled NAND gates and take 2 inverters before after S and R, you get the similar type of truth table. So, this is the logical symbol for this SR latch. Okay. So, we just we give it this is shown like S and R being different values. If we put, then Q and Q bar will be following this truth table value.